Okay, welcome to part 2 of 4. So this part we're going to look at descriptive statistics. So in particular, we're just looking at statistics that we can use to describe our data, make sense of our data, but we're not quite yet at the stage where we're making inferences or any kind of making any significant decisions about what that data entails. So what are descriptive statistics? So this is a way that we use to summarise, large data sets. So you will have seen this before. You'll have seen this in lots of things that we use in day-to-day life. So things like sport, so that on the left is Major League Baseball logo. American sports in particular love their statistics, and these are by and large descriptive statistics. They might have things to do with schools and education. So you see, schools did exams and the average exam grade was this grade, and you compare it to last year, what the average grade were. In particular is the gender gap closing in terms of education in high school. And stock market and finances, particularly right now with everything that's going on with COVID, you see lots and lots of things in the news about how some stock is falling and it's the lowest that it's been ever. It's at a minimum value, it's at a maximum value, and so on. Or the average has changed over each month, whatever it is. So there are a number of different descriptive statistics that are useful to us in terms of how we represent those within research papers and in a way that we can hopefully make sense of them, and then it's up to someone else how they want to interpret. All we can do is summarise the data that we have in front of us. So there are 3 things that descriptive statistics can tell us. They can tell us the central tendency, so that is, where does the data sit in relation to measures of centrality. So for that we're going to use the mean, the median, and the mode. And then it can tell us the measure of spread, so how varied is that data? Is it all kind of clustered around one point, or do we have these outliers either side? And then it can tell us how that data is arranged and what distribution arrangement does it follow. So we call that a normal distribution, where it's kind of symmetrical around the average, or is it skewed towards one or other end of the scale? So what we'll do is we'll just go through each of these things in turn. So if we start with central tendency, we're talking about where the data sits in relation to measures of centrality. So what are those measures that we can use? So I've got some sample data, really simple data. We've just got 7 participants and we've got time on task. And that time is in seconds. And so your first participant was 23 seconds, 14 seconds. They're obviously very simplistic. It's highly unlikely these participants were all exact in terms of their second time on task. But if we use that data, what we can see is we can calculate a mean or an average. So this is the one that you'll be most familiar with. So all we're doing is taking a sum of all the results and we're dividing them by the overall number. And if we do that, what we have there is 20 seconds. So the average time on task for those 7 participants was 20 seconds. Obviously, we've got some participants that are more or less. We can look at the median, which in some way will adjust to that. So we put things in an ordered list and then we pick the middle value. So the middle value in this case is 22. So the median value for those 7 participants is 22. Now let's say I've got another 23 in there. So my median value is going to be 22.5. It's going to be the average of the 2 that are closest. So mean is 20, median is 22, and the last one is the mode. So that is the number that appears most often. And we might use this number when we're interested in, if I randomly sample something from my group of participant data, my data points, my trials, whatever it is, what of those values is the most likely for me to pull out? And so in this case, it's 23. So hopefully what you can kind of see is that we've got 14 and 12, which are quite a bit different than 21 to 25 on the other end. So because of that distribution, each of these values is going to give us something different. And each of those values is used to then determine something different, right? So we when we start to consider and measure the distribution of the data, these values are going to become important. So what is that variation? What's the measure of spread? So what we often want to report is we'll report an average or a mean, but then we want to say, well, that's the mean of this whole range of values. So if I was writing it in a paper, for example, I might say the mean time on task was 20 seconds, and then just put in brackets, minimum was 12. What am I playing at this week? Okay, minimum is 12, and the maximum was some other number, 23. So imagine that those were my ranges. I would have a range of 11 seconds. So that range is important because that range is what kind of tells me, well, how far varied is it? Is it a case that my average was 60 seconds, but my maximum was 400 seconds? Well, that probably means that there's a bit of an outlier there, or the data skewed towards the higher end or towards the lower end. I can use those numbers together to start to build a picture of what that data might look like. So the variance, we've got the range, which is how far away they are, and then we have the variance, which is how far away is each individual number relative to the mean value. And that's important because if I have a very kind of flat curve where I've got data which is spread quite far in terms of the range, I want to know, is that variance actually very wide, or do I have a lot of values in the middle, which is helping to balance that out? And so if I calculate my variance, which we're not worried about how, there is a formula, you can go and look it up if you want, but if I'm calculating the variance, if that number that comes back is larger, then it means that my data is more widely distributed. So if I have two sets of data, I can see which one is kind of less spread out than the other. It's just one part of a big picture that we're trying to build here. So now that I have some variance, I need to somehow standardize that to the data set I use. So mathematically, my variance tells me how far away it is, but it doesn't allow me to apply that to the data set that I'm currently working on. And you do that by calculating a standard deviation. You'll probably see standard deviation used just described as a measure of variance. Unless you're interested in the mathematics behind the stats, you're not going to see the variance calculations at all. But that's just a link in there to a good video to show you how standard deviation might be used, and just maybe put it into a little bit of context for you. So I'm going to show you, but if you want to see it with some more examples, that's a good place to go. So this is an example of two populations. So I have a kind of red colour population, which is that kind of nice peak in the middle, and that has quite a small standard deviation. So the standard deviation of that is 10. So the average in the middle is 100, and its variation is about 10 on either side. Most of the population is within 10. The kind of long flat curve, the blue one, that's much wider. And so the variance from the mean is much more varied because you can see it going out the way. So what does this mean in terms of a standard deviation? So if this is my curve of my population, and at that very top of the curve, now I'm going to assume that these are equal, okay? That's an equal distribution of things that are lower than the mean and things that are higher than the mean. That's a symmetrical curve. 68% of my values will be within one standard deviation. So if my mean is 100 and my standard deviation is 10, 68% of those people will be in a range from 90 to 110. Then, if I look more broadly and start to include those blue parts, 95% are within two standard deviations, -2 and +2, of my mean. And that 95% is kind of a good number, right? Because if I can say that I'm 95% sure that something falls within this part, then I'm probably fairly convinced that it's not going to just happen by accident. More broadly, you see these numbers are just getting lower and lower. So by the time we get to the purple, we're adding 2.35% on either side. Would fit within 3, -3 and +3 standard deviations of the mean. And then a tiny, tiny amount are at the end. So those parts at the end might be sometimes known as the outliers because they're so far away from the middle. Sometimes what you find is you have a little bit of a gap and then one number's like way over there. That's definitely an outlier. So the main thing to take away is that -2 to +2 standard deviations of the mean value are going to give you 95% of all the values in your data set. And then the final thing was about distribution. So this is about the presentation of the data around the mean. So that was what I was shown in that previous example that I've just included at the bottom right there, is I have this kind of nice curve, and that's based on a histogram. So what that curve is based on is those yellow bars on the left-hand chart. So I have between 140 to 150, 150 to 160, and that's the amount of values that are within that range. Now you can kind of manipulate a bell curve in various ways by just making it more, the range is smaller and wider. But what you can do, regardless of how you fit those ranges, is you can draw this kind of nice fit line around the tops of those bars. And if you get something that looks like a bell curve, just the shape of a bell, then you can say that your data is normally distributed. Now, for data to be truly normally distributed, your mean, your median, and your mode need to be the same. What we tend to find is that if things are approximately normal, there are lots of measures that you can use, tests that can check whether or not your data is normal. And if it's not, there's a lot of kind of pre-analysis things that you can do to normalize that or to create more of a bell curve shape. We're not going into it, we're just going to assume that we have a standard best fit. But if you're interested, there's a whole range of stuff about how you prepare your data and ensure that it's normally distributed and what that test is. But this is particularly valuable for things that we know fit a natural range of things. So time, for example, if you think of people who run 5k, there's a large chunk of people who run 5k within a certain range, and then you have a bunch of people who are particularly slow and a bunch of people who are particularly fast. The same with height. We know that the average height is, let's say, 5'10", and then most people are a few inches either side of that, and then we have a few people who are particularly short and a few people who are particularly tall. So all of that together should give us this nice bell curve situation. And typically what we would do is test that and then move on and do our analysis. So that gives you some kind of overview of descriptive statistics in terms of the main things that you need. There are other things that you might be interested in terms of how to display those descriptive statistics. If so, you can go and have a look at box plots, which will display data within different quartiles, which allows you a nice visual comparison of those things. But this is what we need in order to move on to, what's in this presentation is what we need to move on to inferential statistics, which will be coming up next.